preparing to live stream the meeting exercise. The meeting is being live streamed. I can send it to you. Preparing to live stream the meeting exercise. The meeting is being live streamed.
Yeah, I can see the I can see it on the link here.
I can send it to you. To live stream the meeting exercise. The meeting is being live streamed.
So we'll start in 2 minutes.
Yeah,
from now.
sure.
Yeah.
Now I'll try to share my screen. I think you can see me here. Yes, my slide is moving. 1 second. Not moving now. Is
So
it okay?
yes. Yeah, it's working. Yeah.
It's working. Good. Okay.
So I think we should start now, and then if anyone else wants to join, they can join later on, or they can
Yeah,
see the
sure.
recording. So yeah, so this today we are excited to welcome Dr. Ebenezer, who's a resident scientist of the KSO, the Kodaikanal Solar Observatory in India. I had the pleasure of visiting this observatory 2 years ago, and so Dr. Ebenezer is going to speak a little bit about the observatory and hopefully a little bit about maybe some of the observations and some of the work that they do over there. So without further ado, let's welcome Dr. Ebenezer.
Thank you, Timothy, for a good introduction. I'm Ebi. I am presently working as a head of the observatory. Today, I am going to take you virtually to the Kodaikanal Solar Observatory. There you are going to see our telescopes and our exhibits and our research work, what we are doing from our old data and with the present telescopes. This is a virtual visit to British established historical observatory in India. The name of the observatory is called Kodaikanal Solar Observatory. It is a part of Indian Institute of Astrophysics. Our headquarters is based at Bangalore. And today I'm just going to take you to the observatory. Welcome to the Kodaikanal Observatory. This is one of the biggest telescope when we installed here in India way back in the year 1955. And this is our website, Indian Institute of Astrophysics. And this is very much close to the Rose Garden on the way to Kodaikanal. And this is our main gate. And we have a long history for this place from the year 1786. And Thomas Lloyd, he was a director of this one. You might be knowing about Thomas Mirror. And this is olden days, colonial kind of building. Now we converted as a guest house here. And this is our main gate, our main entrance, our Indian Institute of Astrophysics. We have good facilities, like we have the lathes and all the other instruments for maintaining our telescopes. And we can do the drilling on all the mechanical work. We can do it from our observatory. This observatory is located at the highest peak of entire Kodaikanal Palni Hills. The height we can measure is 2,343 meters. And the telescope we enjoy at various sites, we have the different telescopes. Today, I'm going to just give you a brief overview. Then I will be explaining about our observing facilities of old and new. And later I'll be taking through different facilities what we have. We are located almost 3 kilometers from the Kodaikanal. This place is filled with, it's a part of highly elevated place, and it has floras and faunas we have. This wild bisons you can see all the time here, Kodaikanal. And it's a little bit dangerous animals, of course. And we also have the good number of Malabar squirrels, and we have huge size of beehives and other stuff. And this is our observing facility. And now I am taking to the spectral laboratory. The spectral laboratory, it consists of instrument called spectroheliograph. And in this instrument, in the year 1909, January 5th, John Evershed, he discovered there is a flow of gases around the penumbra of the sunspots. And he is John Evershed. John Evershed, he was working on the sunspots. And as you know, that one sunspot have the dark region that we call as umbra. And the circumference of the umbra is filled with penumbra. Penumbra is less magnetically intense regions. And this gentleman, John Evershed, while working with a sunspot, using the spectroheliogram kind of the setup like this, and let me open it for you. He was recording similar, I don't think you can see it. While seeing, I think it is not being focused. This is a spectroheliograms. He was working with that, and he discovered there is a flow of gases around the penumbra of the sunspot that he termed as that is called the John Evershed effect. It is in the literature, and many people around the world working on this John Evershed effect. It's a very famous discovery, and he is John Evershed. He has taken a group of people for the solar eclipse experiment, and he had a very small narrow slit. At the end of the narrow slit, he used to pass through, and we call it a grating. And the grating, you might have heard about it. This is the grating. It is having 1,000 lines. It contains 1,000 lines per millimeter. Such we have a professional. This is all for school experiments, we can use it. And we have a professional gratings in the observatory. And John Evershed, he discovered there's a flow of gases across the penumbra of the sunspots. That already told you. And till the year 1975 or so, in Cambridge, they have used an instrument called Cytostat. And this is one of the rooftop of, or the moving structure we have here. It used to go through the mirror of, we have a achromat lens, and it will be, this is a front silvered mirror that will be, you're seeing somebody, your professor is seeing the front silvered mirror of the Cytostat, this instrument, and it is in operation till from the year 1912 onwards. They used to block the visible photosphere of the light because it is so much bright. So when you block the light artificially, we can see the outer regions, and that we call it prominent structures. It is recorded from the year 1912. So they have recorded the prominent structure using this. This also full disk image of that one can be seen at a green filter, sorry, blue filter that we call 3933 calcium K. And we also have the red color filter that is 6562, that we can see the chromospheric structures that we call the hydrogen alpha. The most abundant gas in the sun atmosphere is hydrogen. To see the chromosphere, though it is only, the thickness is only 30,000 kilometers, one can see the upper and the lower chromospheres using these two filters, like calcium K filters and hydrogen alpha filter. Otherwise, we call 6562.8 filters. This instrument is still, it is in a good working condition. Only drawback is we don't have the films to take the pictures. So the sensitivity that hydrogen alpha filters, the photographic films are no more available. And but we had an observation using this instrument till the year 1999 or so. And H-alpha grating spectrograph also in operation from the year 1911. These two gratings are also with us. This instrument we call a twin spectroheliograph. It produces a 6 centimeter full disk image of the sun. We can take it a white light, and we can use the hydrogen alpha filters, and we can use the calcium K filters, as I already told, showed you at the two different colors. This instrument almost contributed around 75% of our observations in the earlier days. So as you all know that it operates in a very very precise mode. You can see about the vernier caliper kind of the least count one can measure it, and I also showed you the least count from the instrument. It's a very interesting instrument. And we also have the 6-inch telescope that I will show you a little later, the films and other pictures. And as you all know, sun is a 3-dimensional object. When you take the picture or when you take a photograph of that one, it will become a 2-dimension. So we need to do a lot of corrections. Therefore, we have the instrument, we have a small grid kind of a structure that we can overlay on the top of the everyday observations. There we can measure about how many squares or grids it is moving, latitude and longitude, and from the position we can compute the area of the sunspot. That has been done at Kodaikanal Observatory from the year 1904. So more than 100+ years of observation. As you may be knowing, the sunspot cycle lasts for 11.2 years. So we have more than 10 cycles of data we have. So and we can also share it. We can also, the sun goes from the -7 to +7 degrees on the tilt angle that we have used this kind of the tilt angles. These are the very old instrument we have used, and we can duplicate and we can zoom some particular region, and we can also take the particular region and we can remake it. And this instruments we put it in a slide holder. And from the slide holder, I can show it to here at the year 28th July 09 of that is 1909. That is the year, almost 100+ years more earlier. These are the instruments on the effects. You can see from our structures, it is been recorded, and it is a original platelet. Before the advent of the photographic films on the photographic films on the plastic sheets, these are the images they used to take it in the glass plates. And these observations are now it is being digitized. I will tell you a little later about it. Okay, so we can also use the strip chart. These all the these instruments, very old instruments, and we have a comparator kind of the structures. In the olden days, they have used this historical 4-inch telescope. We have used it, and we can also zoom particular region and we can find it out. This heliograph instrument, still it is in a very good working condition. This is a basic optics. We can have it, and the timing is very important in astronomy, as you must be knowing. And to take a very precise timing measurements, we have a John Shelton clock. This is one of the oldest working clock in the world, maybe. And we have a long history for this clock. It has multiple strands, so that the length can be all the time, it will be same. The coefficient of linear expansion because of the thermal expansion can be arrested with this one because of the multiple elements. This clock is still it is in a good working condition. This we call it as a John Shelton clock. It is made by London, and we have many other clocks. It's also one of the golden clocks, and still, but it is not in a working condition. We have other few clocks are there. Let me now take you to the 6-inch and 8-inch telescopes. It is located at the highest peak of our observatory. And this observatory, very recently, it is also renovated, and we still take observations from this telescope. Every single day, for sake of continuity, we are taken the black and white images of the sun, and it is in a good working conditions. And next to that one, we have a 8-inch telescope where it was used by Norman Robert Pogson. N.R. Pogson, he was the director of this place for 30 long years, from the year 1861 to 1890. And this telescope, he used to take the pictures from the Milky Way galaxy, and he started putting the cataloging it. Very interestingly, that catalog, I believe, that is one of the oldest catalog ever made in this entire Asia Pacific region. And this telescope, and you can see that one, it is the results have been published. It is still these books are available in our library. He worked from the year 1861 to 1890, and his name was Norman Robert Pogson. Otherwise, we call him N.R. Pogson. And this book is edited by Charles Mickey Smith. And Charles Mickey Smith, he was also collaborator for this work, and it is printed here in India. Those days, in the year 1892, they called it Madras Provenance, and they published, and this book is available in our Kodaikanal Observatory library. Let me take you to the library. This is one of the before that, let me tell you about the hydrogen alpha telescope. These are the modern telescopes, and the wavelength, it is working at 62.8. And we can see the chromosphere layer using this one. We can also find it out the coronal loops or coronal filaments, and the area of the filaments, everything we can study with this telescope. Nowadays, we are working with a time cadence of 1 minute per day. 1 minute time cadence we are taking. And olden days, they have taken 1 or 2 images per day. But nowadays, we are taking since we are in the digital domain, we used to take plenty of images with the calibrations, like a dark and flat correction. We used to do that one. This is a hydrogen alpha telescope. Every single day, it will be opening like this. Let me give you the, I think sound is not open. I will not share the sound. I'm sorry. This is the way this telescope works in the everyday morning. Now you can see the how it is opening, and it will be pointing our observations towards the sun, and it will be doing the calibration, and it will be having the auto corrections, everything we have. This telescope is a modern telescope, and we used to take from the images from the CCD cameras, 2K by 2K CCD cameras, we used to take these images. And this telescope, it is in functional for the past 8 years. Let me move on to the old data, how we do that. And as you know that we have the legacy of observations from our telescopes, 6-inch telescope for a very, very long time. The first observation started in the year 1902 by Britishers, and later the regular observation started continuing from the year 1904. And this telescope, the construction work, they started in the year 1895, and it was completed in the later days, and they have mounted the telescopes, and we have the observations at least at 4 different layers on the sun. Like we can see the chromosphere of the sun at we're using the hydrogen alpha and the calcium K, and we can also close, or we can artificially occult the visible photosphere, and we can see the outer layer of the sun. We call it as we can study about the prominent structures from the sun. And these are all the new instruments we have. We call it as a digitizer. It has a very high resolution camera, 4K by 4K camera. We used to mount all the old photographic films on the top, and we have digitized, and it is available for the public to use for the research work. Okay, these are meticulously we have collected, and we have identified, just plotted from the year 1921 onwards. You can see that every 11 point is almost 100 years of data we have plotted in the white light, and you can see the sunspot area at a calcium K and hydrogen alpha. These pictures show that the behavior of the sun. Every 11.2 years, the sunspots will be emerging more, and they will go for a decay. Again, they will be emerging again. So we call it sunspot cycle. Synoptic, it is the solar cycle, and how on the long-term variations are happening. We have many people are using our data for studying. This is the sunspot cycle started from the year people started identifying the sunspots from the year 1750 onwards. Now we are crossed the 24th solar cycle and we are entering into the 25th solar cycle. So let me, apart from the solar observation, we also have the observations on comets. And you can see the Halley's comet, which is observed in the year 1906 onwards. And again, it reappeared in the year, you are seeing the picture of the Halley's comet. I think, I'm sorry, it is not, look like it is not being focused. And they have taken the images of the Halley's comet very, very far away. In between the Jupiter and Saturn, they have identified it is a very more like a pointed, very, very small object. And when it came very closer to the sun's atmosphere, and the tail started growing through the process of sublimation, it goes for millions of kilometers. And from our observatory, people have taken, earlier observers, they have taken the ring system of the, you can see the Saturn. It's very interesting to see that. These are the original photographs we have here. We have a huge collection of the data, and as you already know that when comet comes very closer to the sun's atmosphere, it will be the sublimation process happens, and the coma or the nucleus of the comet is just only 30 kilometers or so. But you can see that the tail started growing millions of kilometers when it comes very closer to that. Again, the picture taken at 1910 and 1986, again, the same Halley's comet repeated. We have a good observation. And one of the biggest telescope we have at Kodaikanal is the Kodaikanal Tunnel Telescope. I'll just show to you. This is the original pictures. I had taken it from the archives. In the year 1950s or so, they started constructing and the telescope, and they have mounted everything. And you can also see the mirror system here. It's a 3-mirror system, and the primary mirror all the time it will be rotating at the speed of an earth, so that the image will be all the time it will be constant. It has a 3-mirror system. It's an underground. We can pinpoint its mirror size is approximately around 500 kilograms or so. It's really a very huge structures. For solar observations, this is really sufficient. And the sunspots will be put in a grid, or it will allow to pass through a very small, narrow slit, and it will be fall on the litho type of grating, and the grating will be we can measure the second order or first order, or whichever order we can like, and we can study about the spectral natures of the sun. Spectral natures, or from the different layers from the sun we can take it. Otherwise, we call that as a sun atmosphere. We can measure with a quarter-wave plate or a half-wave plate, and we can measure the polarization from these studies. It will be very useful to measure the magnetic field of the sun at any given position from the sunspot or in the nearby regions. Okay, this is a backside. You are seeing the grating, and let me take you to the next telescope, that is called a White Light Active Region Monitor Telescope. Otherwise, we call that as a WARM telescope. Very interestingly, this is also, it's a homemade telescope, and it's a hydrostat. And this all the time, the primary mirror will be rotating. It's only 60 centimeter small mirror. And this mirror will be sending back the images back to the optical table here. There we have the filters. And we have a beam splitter, which can split the beam into 2 equal parts. One goes to the calcium K, that is 3933. Another one goes to the white light images, we can take it. It is the replica of the images, whatever we have taken from the earlier days. Okay, this warm images, sorry. And these are the images we have, and it is every single day we upload on our website. We can also zoom it to a particular region and we can study about it. We have a twin telescope. The twin telescope is also in operations. And we also had, once upon a time, we had the ionospheric studies at this observatory. Let me quickly take you to our library. It's a very unique collections from the books from the year 17 onwards. It is the uniquely designed telescope. 6-inch telescope. I'm bringing you back to the 6-inch telescope. 6-inch telescope is very unique in design, and every single day, even today, we are operating this single telescope. And already I explained about the John Shelton clock, and the John Shelton clock. We have many things are described in about the observatory is described here. And yeah, John Henry Dalmayer, he was an Anglo-German optician, and he was there in UK for some time. And those days, and he developed this telescope, and in the year 1875, it has been brought to India. It is still with our observatory, and this telescope may not bring any big sciences, but it has a good value, like we can see that one. Now we are planning to put a nighttime another telescope that we call as a DFM telescope, and we also repaired this old telescope observatory sites, and we are not stopped with optical observations alone. We have a radio telescope. Now you are seeing the radio telescope. It is mounted on a cement poles. This can produce. This observation also can see the sun, and this is a polarization studies, and we can study about the flux of the sun at a different wavelengths. Now you can see from the 35 megahertz onwards to 85 megahertz, you can see how nicely the group of type 3 birds are coming. And this all belonging to the shock signatures coming from the sun atmosphere. We call this as a type 2 radio events. And you can see how nicely, and we have many other telescopes. Old telescope is being parked at our museum or a visitor center. And this is a transit telescope. And we can also, now all the old data, we can put it, and we can scan all the data we have. And this is a group of people at Kodaikanal Observatory. It's a very beautiful observatory. And we have multiple. It is a combination of this is a suite of old and new telescopes. So when time permits, you can visit to Kodaikanal Observatory. It's a very it's a unique observatory, and it is we are producing many number of research papers from our observatory. Thank you so much for your patience. Thank you.
Thank you for giving the talk. So one question I had was, you mentioned something about the calibration frames that you use for the telescope. Could you say a little bit about that?
Yes, calibration. In the olden days, all the things are photographic plates. What you are seeing here, these photographic plates with the grain size, it may not be same at every place, and it need to be illuminated by a light source that gives the illumination equal at all the points. Am I right? Like the light photons coming from every place should be equal. That's what we used to do that. And it takes a temperature, it's a very temperature sensitive instrument. Therefore, we need to allow that one halogen lights to glow for almost 1 hour so that it will come to an equilibrium with an atmosphere. There won't be no changes in the temperature. And we used to keep at a very fixed position, and the CCD, the calibration will be, it will be changing. Therefore, we used to take a dark and a flat. Dark means we will completely put in a dark place, and we will, no light source will be there, completely dark. We will close the shutter. Then we will take the measurements, or we will take the 2K by 4K by 4K data, and 4K by 4K data. In principle, every pixel has to give the equal amount of the contribution, but in practical sense, it won't do that. Therefore, we used to do the normalization, and we used to illuminate with a source that we call that a flat. So with a dark and a flat, flat means we'll illuminate with a constant light source. So all the 4K by 4K, again, there won't be no linearity. So dark and flat will be very much useful for calibrating our CCD cameras.
And what sort of wavelengths do you measure using camera?
And with calcium K, we used to work with the 3933 angstrom. And for the hydrogen alpha, as you may be knowing, that most abundant gas in the sun atmosphere is hydrogen. So we used to take the 6562.8, that is a transition from the 3 to 2. That particular line we used to take it. That will be very much useful for us to study about the coronal features on the sun atmosphere. Especially the thin filament will be there. We can measure the area of the filament or lift off of the filament, or the filament, how it is moving upward in the sun atmosphere, or how it is moving in the, if you are measuring from the limb side, how the filaments or the coronal material will be moving out. All these terms with the speed, all the thing we can measure. The solar atmosphere, we know the height, and we also measure with respect to time. Different the time and the distance can give you the speed of the propagation of the materials.
So I went for another talk recently, and they said something about the temperature of the corona being higher than the photosphere, I think. What is the reason for that?
That reason, there are a lot of theories out there that there are a lot of shock waves are there, some chromospheric heating is there. So it is not been resolved yet, and people call that is a $1 million problem, like why solar corona is so hot, or a 1,000,000 degrees solar. The visible photosphere is only 5,800 Kelvin. But the corona, that is ionized corona, is almost 1,000,000 degree. So people yet to resolve, or there are many theories out there, but people still working on coronal heating problems.
Right. Are there any more questions? All right. So yeah, once again, thank you for giving this talk. Yeah, that's pretty much the end of this talk now. Yeah.
Thank you. I think somebody is there and they wanted to ask some questions or something. Dylan, somebody.
Okay, I think we can. Yeah, we can.
I think this. Okay, no problem.
Yeah.
Okay. Thank you so much. I think I have completed within half an hour or so. Am I right?
41 minutes. Yeah, half an hour. We started 10 minutes late.
Yes. Yes.
Yeah.
Okay. Okay.
So if anyone wants to email you or contact you, how can they do that?
Yeah, you can give my number. They can contact me, and if somebody email is also there, I think you know my email.
I don't think I got your email. Is it on some website I can get it?
No, I can give it to you right now. I'll put it in a chat box. I think Dylan also there. My BYMEVE at gmail.com.